Hello, everyone. Thank you for joining and giving us the opportunity to share what we have seen in the last 7 years using carbonic acid to adjust water pH in ag, either conventional or organic operations. We would like to show you how a better water pH control method can help the soil health and also help with people's safety. We will highlight here all the benefits of microbial activity we have documented, either searching for previous research and for what we have seen after switching to a carbonic acid solution from the typical sulfuric acid or sulfur burners. First, I'm from Chile. I've been involved in ag my whole life. First, I was 11 years in fertilizers, and I started doing irrigation design in 1994. All those years designing drip and micro irrigation for ag led me to design fertigation and chemigation systems. And then I designed to install pH control system. And after years of doing pH control systems, I realized the importance of the water quality and what we can do to make it better for the plants and for the soil. Always, and that's a characteristic of us, looking on the simplest way possible. We don't want things complicated. So we have different factors that influence crop management, and water is probably the most important one, especially when it comes to sustainability. We all deal with poor water quality, either it comes from the snow melt, from wells, from the district, doesn't matter. Water quality is most of the time not what we expect, not what our soil and our plant need, and always need our attention. To me, there are 6 important parameters to consider when we look at the sample results. pH, bicarbonates or carbonates, if the water pH is high, residual sodium carbonate, electrical conductivity, sodium absorption ratio, and nutrients. So, as you can see, water pH is in first place because water pH can influence most of those other parameters, making it easier or harder to manage them. We're going to talk only about water pH. That's what we do. We manage water pH. The ideal water pH to irrigate most of the plants is between 6.5 and 7. And we know that the water we have available comes from snowmelt, the mountains, wells. In both cases, water pH is high. Irrigation water here in California is alkaline. Most of the time, pH is above the ideal for our crop, and we need to adjust it to slightly acid. High pH can be a problem for agriculture, either when it's in the water or in the soil. One of the most important problems with high pH in the nutrient is the nutrient availability. If the pH in the nutritive solution in the soil is not the right one, it doesn't matter how much fertilizer we apply. The plant cannot take it, all of it. All those X amount of pounds per acre are not getting to your crop, impacting your yield. You spend a lot of money and inputs hoping to maximize your yield. But if the pH is not the right one, sometimes it's a waste of money. This problem leads also to increased production cost with lower yields, not a good equation for sure. Also, high water pH is responsible for clog emitters because of scale, making water distribution a hassle. Uneven water distribution uniformity leads to waste of water. Some plants receive more water than others, increasing water and energy costs. Let's see how pH influences the nutrient availability in the soil solution. I think most of you guys are familiar with this graph. And you can see in this graph that the pH affects almost all nutrients, from nitrogen and phosphorus to the microbes. Nitrogen, very unpopular today. Excess of nitrogen under water streams, stuff like that, seems to be in trouble at high pH. So an important percentage of it can be taken by the plants. Phosphorus, another major nutrient. The worst scenario regarding its availability is at the most common water pH in the Central Valley, between 8 to 8.5. Iron, responsible for chlorosis on leaves and important to transport oxygen. Manganese influences plant growth and participates in the photosynthesis process. Copper, important for cell wall strength, and is very related to zinc. Zinc, responsible for enzyme activation, helps water intake from the soil, hormones, and temperature control. Boron participates in root elongation, cell wall strength, calcium and phosphate utilization. So in this slide, we can see very clearly how important the solution pH to have all those nutrients, our inputs, available for the plant. Another important issue with the high pH in the water is that usually high pH is associated with high bicarbonates in the water. And as we know, bicarbonates only exist dissolved in water, most of the time responsible for this high water pH. Not always, most of the time. Bicarbonates get into the water when water passes through a calcium carbonate or limestone or magnesium carbonate or dolomite. That's how normally water gets its high concentration of bicarbonates, especially surface water. When applied water dries out, the bicarbonate in it combines with calcium and magnesium in the soil, locking them up. And by consequence, we have less soluble calcium and magnesium available for the plant. Other issues that are the excess of salts it's soil compaction. Soil deflocculates and becomes compacted and crusty, increasing water runoff. Nutrients and salt are tied up into the soil, and they are unavailable for the plant. This last statement bring us to the Justus von Liebig law of the minimum. This German scientist formulated that if one of the essential components of plant nutrition is deficient, plant growth will be poor even when all other essential nutrients are abundant. He represents this law with a barrel. Every important nutrient is represented by a different state. Ones are wider than others, but all of them need to reach the top of the barrel. If only one of them is short, you can only fill the barrel up to the level of the shorter one, limiting your yields, potential, wasting the extra inputs you use to reach the top of the barrel. So, makes sense to take care of everything? This law considers nutrients and also considers pH, water, sunlight, and other important players in plant growth. This law not only applies to plant growth potential, it's been used to model ecosystems, biological population of microorganisms, and a lot of other topics when balance is key to optimize maximum potential. On the previous slide, we have seen that water pH is important and needs attention. Usually, water needs to be acidified. And the most common and widely used methods are either the injection of liquid sulfuric acid directly to the irrigation mainline, or to burn sulfur and mix that sulfur dioxide gas with water to make sulfurous acid. At the end of the day, they are both the same in terms of how they adjust water pH. And it's not common to see these systems having a resulting water pH control loop to adjust the injection of the acid based on the target pH. Without the control loop, you are not sure you are delivering the desired water quality to the plants. I was personally involved in the design and installation of hundreds of systems that use sulfuric acid in Chile, Mexico, and other countries. All those systems had a water pH control loop using pH probe and pH controller. But today, only a few of them are in service. Not because of a bad design and wrong installation, please. We did it good. Mainly because of bad soil health. After a few years applying acid to the soil, and some of them after people get burned and seriously hurt with the acid. These ranches with this system start showing soil turning into dirt, poor microbial activity, and problems with water infiltration. These two methods are still very popular and used left to right here in agriculture. But we believe that this is because not so many people, especially ag professionals, knows that other options are available. Or maybe because sulfuric acid is the cheapest option available, okay? But that lower cost brings other concerns. In the long term, soil health, progressive inputs required, and safety and liabilities. So there's another acid in nature that helps to reduce water pH more efficiently. And it's not new. It occurs every time it rains. And it has been used to reduce water pH for more than 40 or 50 years in industries like wastewater, cooling towers, and to remineralize water after reverse osmosis treatment. Little or nothing has been done in agriculture in the past. But at the same time, those few ag treatments had seen very good agronomic results. They were expensive because they didn't use the CO2 efficiently. Carbonic acid is made when carbon dioxide is fully dissolved in water. Having a pH of 5.5, carbonic acid reduces the water pH in a more natural, safe, and efficient way. Carbonic acid is the most common and natural water acidifier in nature. In the next slide, we can see that carbonic acid is in nature not only as rainwater. It's also one of the methods that roots use to take nutrients from the soil. The plant releases carbon dioxide through the root hairs to make carbonic acid with the water present near the root zone. Then that carbonic acid donates an hydrogen proton with the soil particle to replace it with cations present. And then the new bicarbonate is the one that's going to transport calcium, potassium, copper, magnesium, and other nutrients into the plant. Here we can see that the carbonic acid is key in the natural interaction between the plant and the nutritive solution near the root zone. One important characteristic of carbonic acid is its stability in water. Carbonic acid stays as an acid for long periods of time, releasing the carbon dioxide several hours after reaching the soil. That's what we do at Eco2Mix. We produce the carbonic acid on site with an efficiency close to 100%. No bubbles are going to your crop, only pure liquid carbonic acid. Undissolved bubbles of CO2 are most susceptible to gas off from the water, making the process inefficient and expensive. So, one other factor to consider when we study the carbonic acid as an alternative to adjust water pH is that it's the only carbon-based acid in the market. There is a carbon molecule in the carbonic acid. We have seen this carbon later sequestered into the soil. helping to increase the carbon content in the soil. The carbon is trapped in the soil instead of being released into the atmosphere, and is used by the soil microbiome as a source of food. It's carbon. We're working with several organic growers and operations in the Central Valley and the Central Coast, mainly tomatoes and strawberries. For those operations, we use a non-synthetic carbon dioxide coming from a fermentation process, approved for organic growers. So also, the carbonic acid is part of how forms of carbonate are present in water. They are all pH related. When the pH is high, we have a combination of carbonates and bicarbonates. And you can see in your right side of the slide. When the pH is around 8.5, we have 100% of bicarbonates. But when the pH is around 6.5, we have 50% of bicarbonates and 50% of carbonic acid. For us, this is the sweet spot for water pH for irrigation. With the pH of 6.5, we have almost all the benefits of the carbonic acid and some bicarbonates, totally necessary for nutrient uptake and soil interactions. Our carbonic acid pH range from 0.6 to 5.2. I know I said 5.5, but that's rainwater. That is occurs with the natural circumstances. This is achieved when the CO2 dissolution is made under pressure that is included in our patent ecotomic system. The use of carbonic acid is not recommended to reduce water pH in reservoirs. The CO2 may gas off back to the atmosphere, bringing the pH to its original state and making the treatment expensive. We want you to consider carbonic acid treated water on spray applications. And why is that? Like when you are applying insecticides, fungicides, foliar fertilizers. The water with high concentration of carbonic acid has a lot of benefit for the plant. The carbon dioxide comes straight through the plant, leaves, and stomata, improving photosynthesis, increase plant metabolism, prevent scale formation on leaves, so no white residues after a spray with high alkaline water, increase the nutrient absorption through the leaves, and contributes to the ionization of trace elements in the water. So, to understand better what changes in the soil we have seen after switching to a carbonic acid system, I would like to share some soil test results we have done using a very new method. This soil test is done by a partner company named Biomakers. They have a special DNA sequence test named BeCrop. In this test, they identify most of the soil microorganisms present in the sample and compare them with the huge database they have. And I understand they now have the biggest microorganism database in the world. And that's very impressive. They have operations all over the world. They start in Europe. They group the microorganism and identify different pathways based on the microbial functionality. And to be clear, these results are not the typical soil test. They need to be read carefully. They don't measure actual elements. They measure microorganisms present in the sample, okay? We can help you to that interpretation if one of you likes. Just contact us by email after the webinar and we will be happy to help. At BeCrop, they are expert categorizing the microbial pathway. But it should still be taken as a possibility, not as a fact. Okay, soil sample, the microbiome is very challenging, and there is a lot of research and a lot of contention in the area. That being said, we have seen common trends, and we believe that these are important to share with you guys. We divide this part of the presentation on two types of results. This first one shows changes on microbiome universe on a group of pistachio orchards and the same on almonds. So you can see pistachios on the left, almonds on the right, okay? From samples taken in March 22, spring sample, and August 23, fall sample, after 2 full irrigation seasons, okay? And these are the changes we have seen related to carbon and NPK. So you can see on the carbon fixation, this is to fixate carbon in the soil, the bacteria present that helps on this process grew like 40% or 40 BeCrop score, because it's a scale from 1 to 100. So it's valid to say 40%. And in the almonds, 28%. Just after 2 irrigation seasons. That means, and then later we're going to see how the carbon in the soil content changes. Then in organic nitrogen release, this is the mineralization of the microbes on the nitrogen in the soil. 34% in almonds, very similar in both crops, okay? The phosphorus solubilization, pistachios, 38%, almonds, 36%. Not the phosphorus, is the microorganism that helps with the solubilization of these elements. Potassium, the same, 37%, 36% in almonds. So now you can see that there are changes in the microbial activity. It changes in the microbes in the soil. There are some positive changes on your microbiome. It's not the changes that occurs overnight. These are samples for taken after 2 irrigation seasons completely. And now I'm going to move to a more familiar test. The second group, this is the result of a Haney test. This test, instead of using water extract, they use an acid named H3A. That is a blend of citric acid, malic acid, and oxalic acid. Okay, giving us a better approach to what is really available to the plant. Here, the results are very similar to the obtained on the BeCrop. Great changes on carbon and NPK. So, total organic carbon in parts per million, 44% in pistachios, 25% in almonds. I wanted to highlight here that all these ranches, there are 3 ranches in pistachios and like 7 or 8 ranches in almonds. They are using conventional chemical fertilizers. None of them is organic, none of them is regenerative, no cover crops, nothing. It's typical ranch that you see driving here in the Central Valley, okay? The organic matter. The organic matter grew in pistachios 6%. It's very little. But in almonds, 16%. The average, this is, the numbers are for the average. You can see the deviation that is in each value. So then we have the next one, please. The electrical conductivity. And that gives us an approach what is happening on the chemistry of the soil. And you can see that the electrical conductivity in pistachio was reduced 44%. And on the almonds, 74%. That was impressive, okay? It's an average, but you can see that the first sample on 2022 was way high. So the average was also high compared with the group. If you isolate those 2 on the right, it's going to be less the change, but it's, anyway, shows changes and shows changes in a positive way. Here, other important information that BeCrop give us is the microorganism population and how it changed over time. In this example, for pistachios and almonds, you can see the blue circle are the quantity of unique microorganisms that were in 2022. And the purple one is the 2023 results. So we grew from 392 different microorganisms to 609 in 2023. That's a huge, and it's easy to see in this thing because how big the circle is. And then on the almonds, the change is more moderate than the pistachio, but they're still growing. They change from 1884 to 2021. So there's not too much changes, but there is a clear tendency. The last comparison in this slide shows that the different type of bacteria, fungi, yeast, and other change in the after sample. It's more diverse, it's more microorganisms. If you look at the one on the left, it's 392 organisms, and the light blue are fungi, the tan are bacteria, and those like purple dots are yeast, and there are others. Every one of these circles is a different species. If you look at the one on the right, when we have 609 organisms, you can see that there's more diverse. Even if there are big circles, low circles, there are more circles. That means there's more microorganisms. And also, what we have seen, and every year we improve and we have a better fungi-bacteria ratio. They grow more fungi to balance the bacteria present in the soil. Okay, in the next one slide, the same happened with the almond. Okay, with these results, we can conclude that the use of carbonic acid seems to be going on the right direction. Okay, especially if we're looking to adopt a more sustainable and safe methods to deal with our water quality. Wrapping up this presentation, I want to highlight what changes we have seen using carbonic acid treated water. On the NPK cycling, the microbiome is an important player to release essential nutrients for the plant. Okay, carbon. Soil microbiology helps on carbon sequestration. Okay, organic matter release, and almost all biological process in the soil, creating a better environment for the plant. Carbonic acid treated water has shown a better soil aggregation, improving water penetration, and reducing excessive water runoff. Carbonic acid is eco-friendly and sustainable. There is no other process to reduce water pH that really mimics nature. And last but not least, safety. There are no toxic chemicals to store or to apply to your ranch. No sulfur to burn, no toxic gases, no potential problems with people burning or equipment destroyed by corrosion. We kindly suggest you that you consider your options. If you or your farmers are not controlling the water pH, take a water sample and see what is happening in your water. I hope you can understand the importance of the correct water pH after this presentation. Many times when I'm at the trade shows, I ask people, you have problem with pH? No, I have pure water. I have pure water. I don't understand that because I never found a sample of water that is perfect for the plant. It needs attention anytime. Okay. If you're controlling water pH right now, I encourage you to look at the options and consider switching to a carbonic acid system. It's a proven solution. Check your water pH frequently. It's important. Not at the beginning of the season, at the end of the season. Check, if possible, every other week. It's important. Can make a big change in the optimization of your resources. It's your money. Okay? And thank you very much for your time. And I'm happy to answer any questions that you may have.
Thanks, Waldo. Could you address how acidifying water might be affected by the buffer capacity of the soil?
To acidify the water has the acidification of the water, it has nothing to do with the buffer capacity in the soil. What is going to happen is that acid water of a pH of 6.5, how is going to interact and reduce the soil pH. We have seen in high pH soils a reduction after a couple of years using the carbonic acid system, but also on the opposite, and this is very important, I have seen just for using the carbonic acid and the increase on the microbial activity and increment of the pH when the pH was super low. Like we have a golf course that the pH was 6.2 or something like that. And then after a year, went back to 6.5, 6.6. So it creates like a balance. Even if we're applying an acid, I don't know what they were applying as a fertilizer or other amendments, but we have seen some changes in the pH. But I always give this example. Farming in other countries like Israel, for example, they don't care that much about the soil. They care about the solution, what you have near the root zone, and always talking about the first, I don't know, 8 inches of soil. That is where you have 90% of the roots that are absorbing nutrients and water. I'm not saying that the roots that are below that are not doing that. They're doing, but the most important is in this part. So that's one of the reasons that they irrigate different than us. Okay. But it's important. It's important and can reduce pH, but it's going to provoke other changes, like electrical conductivity, for example. It's leaching some salts. I don't know if that answers the question or.
Yeah, I just was going to say we have a question about the electrical conductivity and a couple questions, but first, somebody asked, wouldn't a strong acid kill off any soil microorganisms of which are becoming more important in nutrient cycling? So I think they were maybe talking about the difference between using a strong acid or a weak acid, or maybe using sulfuric acid injection and how that might affect the soil microbiome.
I have seen personally how the use of sulfuric acid, and it's the same as here. If you compare the carbonic acid providing a water pH of 6.5 to the plant, and sulfuric acid with the pH of 6.5 going to the plant, after a few years of using the sulfuric acid, we have seen the soil turn into dirt. So less microbial activity, less interaction between microbes and the nutrients, and more inputs, because you keep to apply more and more because you don't have microbes that interact with the nutrients. Nothing like that happened with the carbonic acid. Absolutely nothing, because it's like having a slightly acid rainwater all the time that interact with your microbes in the soil better. So the nutrients are better. Some of the results in the Haney test show how much nitrogen savings you have, how much phosphorus savings you have, based on the previous sample with the after sample. And that shows us that you're doing something correctly there.
Awesome. And could you mention the manufacturer of this pH probe? Somebody is curious.
I think that is Blue Lab. Blue Lab, but you can find those pH probes in Amazon easy. I don't buy the cheapest one because my experience is I use them every day. We in Ecotomex, we go and calibrate our pH probe every 4 weeks on all the sites we have. So we have people that goes and check that the pH probe is calibrated and delivering the right pH. Some ranches 6, but I have some ranches with very bad water that we have to go every 2 to 3 weeks because the water was oily coming from the well. So we have to clean that probe and check that everything was okay. You can show some examples of sites that they can see what is a typical installation for a big ranch and for a small ranch. Okay, this is a big ranch. The previous one was almonds. This is pistachios. And we have different setups. Right now, we are attending the strawberry market with this mobile unit that is actually doesn't have wheels, but it's a roll-off trailer that we can move it from one well to the next one at the end of the season. Because of the rotation, we have to move it. So that was key for us to get into the strawberry market. It was the solution for them. So
awesome. We have a few more questions.
Sure.
So what somebody asks, what is going on when the EC drops with carbonic acid? Is this an elimination of bicarbonates?
I don't think so. I don't think that is an elimination of bicarbonate. I think there's an elimination or making a lot of different salts that influence the electrical conductivity more soluble and can be either utilized by the bacteria in the soil, because one of the things that we are not sure, but we did not did a test like that, like measuring the electrical conductivity at different depth to see if we are moving the salts down or we are making them available so the microorganism use them. Okay, so for sure, I know we reduce sodium and we take samples in the first 6 inches of the soil. Okay, we reduce sodium, we reduce chloride, we reduce the electrical conductivity in those samples. So for sure, those are the ones more affecting the electrical conductivity. Bicarbonate, for sure, is more soluble. It depends on the bicarbonate. Actually, when you have a carbonate and you react with carbonic acid, you form a bicarbonate that is way more soluble than the carbonate itself.
Awesome. So what effect, I mean, this is kind of related to that, what effect does carbonic acid have on free lime in the soil?
It's exactly what I just said. Free lime is calcium carbonate. It's going to react with it and make it a bicarbonate, but a bicarbonate that is more soluble. So if you have a calcium bicarbonate or a magnesium bicarbonate, remember that when it's soluble in water, the plant can take that calcium, the plant can take that magnesium. Is the way that I show in one of the slides how the plant take it. The fear from farmers most of the time is when you have an excess of salts and bicarbonates coming from the water and they do not do nothing, they start accumulating this because it's still the soil and the solution near the root is not the right pH. So there is no potential interaction with the roots on the plant, right?
So next question.
I don't know if that answered the question or not. So please feel free to keep asking.
Awesome. So are you injecting carbonic acid or CO2, which converts the calcium bicarbonates into carbonic acid and calcium?
Can you read it again, the big question?
Yeah, let's see. So the question is if we are injecting carbonic acid or CO2, which is the one that converts calcium bicarbonates into carbonic acid and calcium?
Okay, okay, fine. No, okay. How the system works, it's easy. You have your filter station. In that picture, for example, you can see that we have the filters, and then you have 2 elbows going underground. In each of these elbows, you can see a small PVC pipe. That pipe goes straight to the input or the inlet of one of those Eco2Mix boxes. So in that box, we read the pH. That means we are reading the pH of the water that is going to the field. We read the pH, we inject the carbon dioxide inside the machine. Through different process, we dissolve the CO2 and make carbonic acid. In part of the process, we also get rid of the bubbles, take those excess undissolved bubbles, we don't want it. We redissolve it, recycle, put it back into the stream that we have there, and only carbonic acid is coming out of the box and is going upstream the injection point, like where the middle of those filters are, you have the injection of the carbonic acid that is blends with the rest of the water. So from the injection point that is coming with the pH of 5, blends with the raw water that in this case has a pH of 8.6 or 8.7. And then we take a sample again. So we take water to produce carbonic acid, we inject the CO2 and re-inject it upstream. Because as I said before, it's not corrosive. We can do this loop of the carbonic acid. And we inject carbon dioxide to produce the carbonic acid. but the injection of the CO2 is driven by the pH result of that treatment.
Awesome. And actually, that kind of addresses this other question, which was, what is the method of producing carbonic acid on site? And I think that addresses
I
that
just
well.
said dissolving carbon dioxide in water in an efficient way, or grab a cup, put it outside when it's raining, and you have carbonic acid too.
Well, so can this kind of system be used for a non-pressurized system? For example, a corn on flood situation?
We can use it, but I don't recommend it, but it's going to be super expensive because we try to use under pressure. We can produce the carbonic acid in a canal, or we can treat the water on a reservoir. But as I said in the presentation, few hours after, that CO2 is going to balance with the atmosphere, both pressure balance, and the CO2 is going to go back to the atmosphere. The key is do it in drip, micro sprinklers, pivots. All those systems can be treat the water. We treat the water on all those types of pressurized systems. So they deliver the water with the carbonic acid close to the plant, and then the infiltration rate is different. So the water goes down, and several hours after, that CO2 is going to be separate from the water, but it's going to stay there. It's carbon dioxide. It's part of the respiration process of the microbiomes.
These are some great questions. We've got two more here, but if you have any other questions, you're welcome to send them in and we'll address them. So Waldo, does your irrigation water quality influence the efficacy of the CO2 injection? For instance, elevated EC or bicarbs?
Yes, because in this case, we're talking about the buffer capacity in the water, right? It influences when we budget a system for a customer. And by the way, we don't sell the equipment. We are a company that provides a service. We treat all those equipment that you're seeing in that photo, the white tank and the two boxes, it's our assets. We bring it to treat the water for the farmer. They don't have to pay for that. They don't have to do an investment or a capex. Okay. Going back to this, I always ask for a water sample that has to have the basics: pH and bicarbonates or alkalinity. With that, we can budget a certain amount of carbon dioxide per gallon, per acre foot, whatever. And you give me, okay, I have 300 acres and I'm planning to use 3 acre feet of water. So I have to treat during the year 900 feet of water. And that's why we provide you with the pricing for those 900. And that is going to tell us how big the CO2 tanks need to be. The eco-to-mix are exactly the same for 50 gallons per minute, for 500 gallons per minute to 5,000 gallons per minute. Doesn't matter. It's the same equipment.
So regarding the CO2 like that we see in the tanks here, is that something that we're making on site or bringing in by truck?
We bring it on by truck to fill those tanks. Those tanks are pressurized. Actually, that tank that is there, the white one, is 350 psi of liquid CO2. If we try to store gas CO2, no, it make no sense, and it's make the system absolutely unaffordable. We have to store liquid CO2 because we have more pounds per store at the site. That tank himself stores 12,000 pounds of liquid CO2. And you can see in the back, there is a vaporizer, and we add a couple of extra vaporizers to be sure that we are putting in the system only gas, CO2 gas into the system. We don't want the CO2 liquid because CO2 liquid can freeze.
All right, so one last question we have here. If you have any other questions, anything you're curious about, you're welcome to ask them. Oh, and here's another one. Okay, so this question is about the cost per acre on a pistachio block in Firebaugh. And you mentioned there's a couple factors that go into a cost. Maybe you can talk about what some of those factors are and how that's calculated.
That ranch in particular is in Fireball. This is 650 acres of pistachio. It has 2 filter stations, so we have one system per each, but they're sharing the carbon dioxide tank. I believe they are paying around 110, maybe $108 per acre per year. Everything is included. And the budget for that was about like 2.5 acre feet of water. In the previous one, the one in Modesto, 1,300 acres of almonds, they use maybe 2.5 acre feet of water. And because it was 1,300 acres with the same assets, they were paying less than $100 per acre, for sure.
All right, so this is another question that relates to pistachios and cost. First, would using subsurface irrigation help conserve your input, little or no evaporation? And what is the typical cost per acre for pistachios? I think you addressed that.
I addressed that, but it's a good question about the subsurface drip. And that's much better because the water is going to be delivered to the root zone under the soil. So we don't have any loss of water. So when you have subsurface drip irrigation, you should be using less water than with the same drip line, but on top of the soil, because you have a better distribution of the bulk of water, okay? And you have some distribution going up and a lot of better distribution going down. You don't have this waste of water on top for evaporation, especially in summer here in the Central Valley. Even if the soil with the water is lower temperature, they're still high. There's still some kind of loss for evaporation. And the system can work perfectly. On the tomatoes, we have all of the system are with sulfur tape.
This is the question was asked by, and this will be our last question. The question was asked by Walter.
It's okay. I have to go to the Home Depot like 4. So I have time.
Okay. All right. Well, if we can kind of call it as an end, and if anybody wants to keep asking questions, you're welcome to.
Sure.
That last question was from Walter Peterson that wants to note that he represents Deep Root Irrigation.
Okay, I know them.
So he also mentions he asks about maybe a basin, how a basin would be different from subsurface irrigation. I'm not sure exactly how that relates.
I don't understand the question. Can you elaborate a little bit more?
Let's see. I guess I'm not quite sure. So you just said basin being different from subsurface, Southern California, Bakersfield area pistachios. I might be referring to the difference in area. I'm not sure.
Maybe it's referred to the water quality. We have system installed from Sacramento all the way to the
price even. I think he's because Fireball has cheaper water.
The price is the same because the water is cheap. I don't influence. I have no influence on the water. How much you're paying for the water. If you are paying cheap for the water, maybe you can spend more money on treat that water better to have better yields. That's what I guess. A farmer that is paying $1,000 per acre foot of water, I think it's going to be a tough decision for them to use a system that increase the cost to production cost for them. But it's more related with the water quality than the cost of the water. Okay, because the treatment I have to do it anyway, and all the time I'm going to try. Sometimes if they want like a more affordable price, sometimes there are farmers that are willing to consider us like say instead of 6.5, can you do it 6.7? 6.7 is way cheaper than 6.5. And 6.5 is way cheaper than a 6.2, because as you know, the pH is a logarithm from the previous number, so it's 10 times bigger. So I use 3 times more CO2 to treat the water to reach pH 6.5 than 6.2. So I show them options to the farmers, and they decide to go 6.2, and sometimes says, hey, you know what? I'm seeing good results. Why don't we go 6.7 to make it a little bit cheaper? No problem. Just calibrate the system again at 6.7, and the system is going to deliver 6.7. It's going to use less CO2.
Awesome. Okay, well, thank you all for coming and for your great questions. The contact information is here. Welcome to give us a call or send us an email. Yes, there's one quick question that just came in. Can this be used in conjunction with fertigation?
Yes, absolutely.
Yeah,
absolutely. The carbonic acid water, treated water, is compatible with any fertilizer, pesticide, fungicide. And as I said before, I encourage you to use it, the treated water, on your spray applications. It's like using rainwater along with your irrigation water. So there's no conflict. We are not accumulating sulfates in the soil. There is no incompatibility between these calcium and sulfur or stuff like that. Absolutely compatible with any fertigation system. That's how I started. I did fertigation system like more than 20 years ago. I started doing that. But right now we do only water pH control using carbonic acid. That's the only thing we do. Nothing else.
Awesome.
I appreciate
I think that same person mentioned that they're getting good yields at 1.3 acre foot.
Yeah, that's awesome. What I'm saying. So it's sometimes I have seen a lot of waste of water here that sometimes you get not much yield increasing the water cost. But if you do it efficiently, like pulse irrigation, better control of the soil moisture, using probes, and keeping in the right levels all the water, you can save a lot of money in water, and at the same time keeping the same yield. And if that water is the best quality, because it's less water, it's going to cost you less to treat that water with the carbonic acid.
Awesome. Well, thank you everybody for coming. You're welcome to reach out if you have any other questions. We'd love to talk more. We appreciate you learning about carbonic acid with us.
I want to say thank you. We really appreciate this. It's been fun. This has been 7 years of a fun ride. Okay, join us. Thank you.